there's two people here. Let me give people a little more time to get in. Giving folks another minute. All right. Hi, everyone. We're headed into the home stretch of this class. We've covered a lot of ground this semester. We've talked all about Haskell, and then we, looked at all sorts of implementation and design considerations for more conventional object-oriented imperative languages. And we're now going to return a little bit to our roots and talk a bit about a topic which spans both functional and imperative languages, namely concurrency. And the theme of this week is sort of going to be about what languages like Haskell can teach us about, how to write concurrent programs in a scalable and understandable way. We'll also, of course, talk a bit about how concurrency is worked with in normal languages as well, and that's going to be what today's lecture is going to be all about. And on Wednesday, we're going to look at this very fancy idea called software transactional memory. So look forward to that. And also, I've released the very last graded homework for this class, the Concurrency Lab. It's in JavaScript. And it's also going to be a throwback to your continuation passing days. So if you thought you were free from CPSing your code by hand, sorry, you're going to have to do it at least one more time with today's homework. Okay, so to start off, I just want to ask a much more basic question, which is, what is concurrency? When I talk about, dealing with concurrent situations when writing computer programs, what do I mean by this? Okay, if this were a physical class, I would actually ask people to tell me things. Here are some common quotes that I get when I talk about concurrency. One is that, concurrency is when you have multiple threads being, some sort of operating system or programming language abstraction that lets you run multiple things at the same time. So that's like another thing that I get when people tell me this. And these are all very reasonable ways to intuitively think about concurrency. And my job is not really here to give you a formal definition of concurrency, but this is the kind of thing we're going to be talking about when we talk about concurrency in this lecture. The next question I like to ask is, why bother writing concurrent software? If you've ever written a program that, for example, uses threads, you may have noticed that it's a lot harder to write your code in this situation. And so this reasonably asks, one might reasonably ask, hey, if concurrency is so hard to write correctly, if it's so hard to do, can we just write programs that are not concurrent? And a lot of the time, the answer is yes, right? For example, all of the Haskell programs and all of the labs we did in this class, they were all deterministic. They were not concurrent, and you just wrote a program and it executed line by line, and that was perfectly acceptable. But of course, there are situations where you have to deal with concurrency. There's no way around it, right? Your computer itself, right, as it's executing, is concurrent. It's concurrently executing tons of different programs all at the same time, multiplexing between them. They're all running at the same time. They might all be contending for the same resources. And if you're writing an operating system, or even if you're writing, some sort of moderately complicated piece of software where, you can have lots of things going on at the same time, you don't have a choice, right? You're going to have some amount of concurrency in your language, and you've got to deal with it somehow. And of course, the other big problem is, software doesn't live in a black box and only give off heat as it's executing, right? It lives embedded inside of the real world. And in the real world, right, there's tons of things going on all at the same time. If we want software to be able to usefully model the real world, to be usefully able to interact with the real world, we have to actually be able to deal with this very important thing that is that things can happen at the same time in the real world. So we want software to be useful, and that means that we've got to deal with it. So the central question in this class, and we're going to be exploring it this week, is how can programming languages make concurrent programming easier, right? And in particular, like the sub-question we'll ask here is, what abstractions are the most effective at making concurrency easier? Now, we can try to handle the abstractions necessary for concurrency purely as a software library concern, right? So someone writes a programming language, they pay no attention to concurrency, and then in some situations, it may be possible to write a bunch of libraries that let you deal with concurrency in a reasonable way. And we'll look at a few examples of people having done this. But in general, it's very hard to write good abstractions for concurrent programming. And we'll often need the extra tools that a programming language gives us to actually, get something that is at all reasonable. And we'll be looking at a few different systems for doing concurrency in various programming languages. Now, I keep saying concurrency is hard, and I said, if you've ever written a multi-threaded program, it's very hard to write them correctly. And one question you might ask is, well, why is concurrent programming so difficult? And there's a lot of things, right? Like, for example, concurrent programs can be non-deterministic. So that means that, when you run your program once, it passes, and then you run it again and it crashes, right? Everyone hates that sort of situation because you just don't know if you've actually fixed the bug or if you made it happen way less frequently. But there's another thing that I want to mention here, which is that what makes concurrency really difficult, in my opinion, is the fact that it smashes through abstraction barriers. Due to timing constraints, this semester I didn't actually give my lecture on modularity. Maybe that'll be the bonus lecture this year. But when we talk about programming languages, and in particular when we talked about object-oriented programming, we did spend a bit of time talking about how one of the primary ingredients about OO was this idea of encapsulation. That is to say, we could write a class and we could hide some private data on the inside of it, and people wouldn't be able to access that data without actually going through the class itself. And in that sense, the data was abstract. We could refactor it, we could change it without worrying about affecting the external world. Concurrency flips this on its head. It actually makes it possible to observe the internal implementation details of all sorts of things if you aren't careful. And so that makes it really difficult because basically all the tools we have for understanding big software systems, they're all about information hiding. They're all about, you don't have to care about how that component works. You just can treat it as a black box and use it in some way and everything will work out. Well, that's a great strategy most of the time, but when you're trying to do concurrent programming, you're going to have to work really hard because a lot of implementation details start leaking out in this setting. So where are we going with this lecture? So once again, when we talk about abstractions for dealing with concurrent programming, there's multiple levels of abstraction. So at the very lowest level, there's this thing called a memory model. What the memory model does is it basically says, hey, I have a processor or I have a VM with bytecode. And I need to define at a very most basic level what behavior is possible to observe versus not, right? Like I've got my silicon, it's got multiple cores on it, accessing the same main memory. If I feed it a bunch of instructions on the cores executing at the same time, I need to be able to say something about what actually can happen. Because if the answer is anything can happen when you have concurrent programming, that's just not useful, right? We wouldn't be able to program cores in this way. And our processors and our VMs do give certain amounts of guarantees They give less guarantees than you might hope sometimes, but they do give some guarantees. And those guarantees are the basis by which we can build higher level abstractions for concurrency. The next level up in the abstraction barrier, I would say, are locks. Locks are sort of the bread and butter of concurrency. They're very simple to explain, very simple to understand. They're not very compositional. They have some problems, and we'll talk about them in more detail. And then finally, on top of that, we have sort of what I'd call high-level concurrency abstractions. So some of these are not very much different from locking. For example, in Java, concurrency centers around these things called monitors and synchronized blocks. And honestly, they're very... They're just a little bit higher level than locks. But then you also have super higher level ideas like message passing, which eschews the ability to like have mutable shared state at all, or transactional memory, which we're going to talk about on Wednesday, where it totally abstracts over the idea of concurrency, and all it says is, well, tell me what set of operations you want to happen atomically as a unit, and then I will make it so. So, there's all these different levels, and we're going to talk about all of them in today's lecture. So the basic problem of concurrency is that we have a bunch of concurrent threads. They're all running at the same time. And if all of these threads were just running by themselves without talking to each other, without contending over some sort of shared resource, in this case, I don't know what this is. This is a soup line, I guess, during the Great Depression. Contending over that shared resource, then everything would be fine, right? Like you just, reason about each thread independently. And it is only when they are trying to access the same shared resource, that's when all the problems of concurrency occur. Because now we have to talk about how these concurrent threads of execution interact. So to give a very basic example, this is a classic example. It's you're writing a banking system, and so you've got some shared memory. That's the balance. That's the account balance on someone's account. And you've got two people trying to access this balance at the same time. Maybe one thread is trying to withdraw $100 from the account, and another thread is trying to withdraw $50 from the account. And basically we want to check if you have enough funds to do the withdrawal, otherwise give an error in this case. And so the classic problem, So the classic problem that arises when you write some code like this is if these threads are running at the same time, there's a potential for a race. And the race looks something like, well, thread 1 and thread 2 could both test if there's enough money in the shared account. Thread 1 would say, oh yeah, the balance is 100, so there's enough money. And thread 2 would say, oh yeah, there's enough. There's 100 in the account. That's enough for 50. And then they would both attempt to simultaneously extract money from the balance. And assuming this doesn't data race, you would end up with negative 50 balance, which probably is not good for the bank, which doesn't want you to have a negative balance in the situation. And so, people have known this was a problem for a long time. And, like Dijkstra in 1965 was like, yeah, so this is a problem. And, the way we should deal with this is let's define a sort of critical region where at any moment only one of the processes is in its critical section. This concept of critical region exists even today. So really this stuff hasn't changed since then. So instead of having everyone trying to get at the shared resource all at the same time, we only let one thread in. That thread during the critical region gets to interact with the resource, and then we have a bunch of threads waiting for us. And the basic mechanism for doing this is a lock. So this is like kind of the bread, right? So this is the earliest concurrency mechanism, and it's a simple one. And I think you should have already seen this in other classes that you've been taking. So, Dijkstra was like, hey, we should make sure only one thread gets to be in a critical region at a time. You ask Dijkstra, well, how do I do this? And Dijkstra's like, okay, let's come up with this concept of a lock. And the rest of the paper that this comes from basically is showing you how to define a lock. It's not that relevant today, but hey, locks are a good idea. So I don't know, we could just be like, hey, okay, so we got concurrent programs. They're trying to access the same data. We need to make sure that doesn't happen. So let's slap on a lock. And is that it? Are we done? Can we go home? Right? Like just we tell people how to use locks. We tell them, yeah, when you access shared memory, just use a lock, and then they can write bug-free concurrent code. Well, if only this was so simple, right? So let's look at a few problems. So one question that arises when you tell some poor unsuspecting programmer, hey, I need you to make your code concurrent, go add some locks, is they'll be like, okay, where do I put the locks, right? So in this example, I've got two threads accessing X and Y. Thread 1 says, okay, I'm going to take out a lock and then increment X and increment Y, and then release the lock at that point, right? So great, it's code. It uses a lock. Is that always going to be right? Well, no, because locking is just not something you can just do. It takes two to lock, right? Not only do you need to take out a lock, but anyone else accessing the shared state has to respect that lock by also taking out the lock. So this code, right, is not really correct. We can end up with a race in the situation because thread 2 isn't actually looking at the lock. So already, there's this extra constraint when you're writing your locked code, which is, well, I need to think about what resources I'm accessing. And then whenever I access those resources, I have to make sure I take out the lock associated with those resources. And you're writing this in C, really all C does is it lets you implement a lock, and it doesn't really give you any extra help in this situation. So you basically, when you're working on multi-threaded code in C, you have to know what every variable is. Is it a local variable, so you don't need to lock it? Is it a shared variable over multiple threads? Then you do need to lock it, and you need to know what lock is associated with every one of them. It's a mess, right? You have to be thinking about all of this constantly when writing multi-threaded code in C. And there's even one more question, which is say I leave out the locks, right? Well, your program's still going to do something. What is it going to do? And that's a question you really can only answer with a memory model. Okay, so let's say that we know we need locks, and we know we need to associate resources with locks, and I wrote that in my guidebook, and people start happily writing locking code. Well, there's more problems, right? So we don't only care about our programs being correct, our programs not having data races. We also care about our programs performing fast and not falling over when our website hits front page on Hacker News and tons of traffic comes to it. So there's another problem with locking, which is how do I schedule requests, right? Let's say that I have one thread which is a super high priority request, right? And I need to make sure it actually gets serviced. And I don't want it to be waiting for some very slow, maybe batch processing thread, which is going to take a bunch of time to finish before I can service this request, right? In order for me to keep latency low, I need some way of saying, well, this guy should get priority over some other guy who's trying to get to the thread. And so in this example, we have another example where thread 2 is not as high priority, right? It's I only need to run. Oh, sorry. So thread 2 is a different situation. Thread 2 is it's waiting for a lock, but instead of wanting the lock immediately, thread 2 only wants the lock if some buffer is empty or non-empty, say. If the thread is trying to read out some data, it might want to say something like, well, I don't want this data. Sorry, don't let me into the critical region until you actually have some data, because otherwise I will just uselessly, get into the region and be like, there's nothing to do, and then get out of the region again, and thrash your CPU in the process. So there's this problem, right, which is that we can't just do locks to enforce mutual exclusion. We also need some degree of control over controlling when threads should run, because either there's a high priority thread that needs to run fast, or because there is a thread that wants to get woken up when some computation actually happens. Okay, so it turns out there's a name for that thing that I talked about here. Well, for the thread 2 situation, you just want a condition variable that's like a library abstraction you can add. And, about priority, well, there's also ways to do that as well. So you put all that in the handbook and you're like, okay, now we can write concurrent code that's correct. And, your programmers start sending you programs that, work okay for a bit, and then they just mysteriously hang. And they just don't ever get back to you. And why is that happening? Well, probably what's happening is there's some sort of deadlock in your program. So here's a simple example of some innocuous looking code that can produce a deadlock. The thing that's so innocuous about this code is that independently, these two threads are correct, right? So thread 1 takes out the first lock, then takes out the second lock, and then does some stuff, and then releases those locks. Because remember, we said locks are associated with resources, and therefore, I need to take out a lock for a given resource. And in this case, we need to access both 1 and 2. So thread 1's code is perfectly fine. Thread 2's code is also technically perfectly fine. It just takes up the lock for 2 first rather than 1. But now we have a deadlock. So the deadlock is thread 1 takes out a lock for 1. Simultaneously, thread 2 takes out the lock for 2. And now thread 1 has to stop. Thread 1 stops because it can't take out the lock for 2 because thread 2 has it already. But when is thread 2 going to release its lock? Well, it's waiting for the lock from thread 1, but thread 1's holding it. So they're both blocked on each other. No progress can be made, and your program just hangs infinitely. So it's not very compositional, right? You have to know something about the ordering of your locks, or you have to have some sort of global discipline. For example, you could say, well, there's only a finite number of locks in my system, and so here's the order you have to take out the locks in. And then if every region abides by that order, then you can't have a deadlock. But you have to do something like that, right? Not very compositional. So I've told you all about all sorts of horrible things that can happen when you're just using locks to enforce mutual exclusion. And this would not be a very good programming languages class if I wasn't like, okay, well, we can make your life easier by introducing some programming languages concepts to the mix. Before I get there, are there any questions about locking or any of the problems that I described? These are all classic problems, so you've probably seen them before. Okay, so let's take a look at what tools we've got in the PL box to help make this better. So the first thing I want to talk about is not that much of a step from locks, but it's very illustrative to look at because what basically has happened is Java has taken the basic idea of locks and built in a little bit of syntax sugar to the language, built in a little bit of convention to turn it into something that is sort of basically usable by people. So here's the basic concept. So these are called monitors. And so the way that you will typically do basic locking in Java is you won't actually allocate an explicit lock object, although you can if you want. Instead, you will use this special keyword called synchronized. So what synchronized does is when you write a method on a Java class, you can put this synchronized keyword on it. And that just means that well, at a high level, it means you can run it in a concurrent context. So you would basically, write synchronized methods for methods you want it to be thread safe. And then on the inside of the functions and questions, there's also two other methods which are available on all objects called wait and notify. And as their name suggests, when you call wait, you suspend the execution of the thread and don't do anything until someone else calls notify on the very same object. And that basically says, okay, go ahead and keep running after the wait. So in this code sample here, we have a very simple, locked queue. And what this queue is doing, right, is if I want to send some data, I just enter the synchronized region. That's the critical region, taking out a lock on the object in question. And then I push something onto the queue. And then I notify any thread that called recv and was waiting for an object off the queue to, keep going. And what it'll be able to do is pop that element off the queue, once again, inside the lock and return it to you. So at a high level, this makes sense. Let's dig into a little more detail about how the semantics for monitors work. So the model for monitors is the same good old idea with object-oriented programming, right? Which is that our objects are the idea of encapsulation. are the mechanism for providing encapsulation for the data in question. So normally we have methods that let us interpose on accesses to private state in the object. And we have now another layer, which is the monitor that's controlled by the synchronize call. So let's say that I want to access data through the send method. I want to call the send method on this object. So the first thing I have to do is I have to ask the monitor, because this is a synchronized method, hey, can I actually operate on this object? And there's a lock associated with every object. And so if there is someone already with the lock on the object in question, that will block the caller until the lock is freed. So now if monitor has the lock, we go ahead and we take the lock, so no one else is allowed to lock the object, and we just go ahead and execute the code inside the send method as normal, but holding the lock on the object in question. And now let's say that we call the recv method instead, so we're going to try to receive some data. This time, we will get into the object. Let's say that there's no one out with a lock. But then what happens is we basically want to block until there's data available for us. So that's what the wait operation is for. And essentially, when I say wait on the inside of the object, I'm saying, hey, I can't actually finish processing this request right now. I'm going to wait until there's some data available, until someone else calls notify on the object. So a common situation for using this sort of pattern is when you have some sort of producer-consumer situation where you've got this buffer and there's a lot of producers trying to write into the buffer, and then you have a lot of concurrent consumers trying to consume for the buffer. So all these consumers are pulling stuff off the buffer, as fast as they can, but if there's nothing in the buffer, they just need to wait until some data actually gets produced by the producer. So the way this actually is implemented is you get out the lock. Sorry, I said this already. Let me just go through the slides. You get out the lock, you run the code in recv. Recv calls wait, there's no data. And so now what will happen is we will return the lock. So we will release the lock and suspend the caller, waiting until some data actually happens. And so when caller 2 actually sends some data, they put some data on the queue, it says, okay, hey guy who was suspended, wake up. Actually, there's some data now. I'm going to notify you about it so you can reacquire the lock once I'm done executing the method and get the data in question. So another way of doing this, okay, there's a question which is, does notify release the lock? And I believe the answer is no, notify does not release the lock. So what you do is you finish executing the synchronized block, and then the thread that was notified actually gets to reacquire the lock and get going. So here's another pictorial diagram of what's going on here. So I've got this thread accessing some object, and there's some number of waiting threads which are waiting for data on the object. And so when the thread calls wait on the object in question, this thread gets put onto the waiting threads queue. So it's not executing, and in fact, we can have lots of threads waiting on the same object in question, right? Like, for example, in the multiple consumers case, if the buffer empties out, then all of the threads will end up waiting for new data in question. And then there's there's actually two methods in Java. So notify just says, hey, take one thread and start executing it. Well, start executing it when the lock becomes available. And there's also another method called notify all, and what notify all does is it actually goes ahead and executes all of the threads, lets all of the threads that were waiting start executing again. And of course, they may not actually start executing concurrently because they're going to be inside a synchronized block, and so they still have to take out the lock on the object. But certainly after thread 2 is done processing, it'll release the lock, and then thread 3 can start going. And which of notify or notify all you should use, that is entirely application dependent, right? So for example, in the recv situation, in the send situation, I'm only pushing one object onto the queue. So I only really need to have, wake up one thread, because one thread is they're going to be able to get in this situation. But in some other situations, you might, have a bunch of people waiting for some event, and then they all can go once that event happens. And then in that case, you would use notify all. So to briefly summarize monitors in Java, so this is still shared memory concurrency. So there's private data, and that private data can be shared across threads. So it's your responsibility to know when an object can get shared across threads, and then you actually have to go ahead and put synchronize on the methods to make sure they're actually synchronized. Java implicitly associates every object with a lock. So you don't actually have to define any locks. You can always lock on the object in question because, remember, locks are all about preserving data. So we want to associate a lock with the data. And then, there's the keyword synchronized, and then a bunch of methods, wait, notify, and notify all, that tell you how to interact with things. Note that Java's type system doesn't interact with concurrency at all. So you basically have to read the documentation to know sort of what the right way to use various methods are. So there's a question which is, so only up to one lock per object in Java? And the answer to that question is Java will implicitly associate every object with a lock. And of course, you're welcome to allocate new locks using the lock class, and you can block on those certainly, but you get one lock by default. So monitors are a very simple implementation. Hang on, there's another question. So the object has a hidden lock that's important for methods labeled synchronized, but you don't have to use wait, notify, notify all, but they can still be useful for certain situations. So let me see, how do I answer for that? So yes, there's a lock, and you don't have to say anything. It's implicitly defined. And then if you use synchronize, that's what the synchronized blocks are taking out locks on. And yes, you don't have to use wait or notify all. They're specifically useful for scheduling situations where not only do you need to make sure there's no concurrent access, but maybe you need to actually wait for some data to be available before you can keep going. So it's all about, the ability to block and wait for data for later. Okay, so Java locks are very simple to implement. They, don't have they're not that complicated. They don't do that much for you, right? There's a lock, and then there's this wait, notify business. And because they're so simple, there's actually some problems with them. There are some ways you can easily shoot yourself in the foot just using synchronized blocks in Java. So here's one example. I've used a little bit of extra syntax here. So when you put a synchronize keyword on a method, that takes out the lock on an object. You can also use synchronize as a bare block. And so what I'm just saying here is synchronize A says, take out the lock that's defined on A. So this problem called nested monitor lockout occurs when you take out a lock on A, take out a lock on B, and then try to wait on A. So what does this look like? So what this looks like is, what's going on here is we said what the definition of wait was, right? So the definition of wait was when I wait, I need to go ahead and return the lock and wait, right? Returning the lock is important because I don't know returning the lock is important because I need to be able to run other code on the inside of B, which is going to be actually responsible for example, notifying me that I need to unlock myself, right? So I need to return the lock for B. And so Java knows when you call wait to release the lock from B. But what's going on here is there's actually two levels of monitors going on. And Java opted for a very simple implementation of wait. And all wait does is it releases the lock on the object that you called wait on. And so in this situation where I had taken out a lock on A first, before I started calling into methods for B, B knows nothing about A. B doesn't know that you are holding onto the lock for A. So it has suspended the thread. It has correctly released the lock for B, but it hasn't released the lock for A. So actually you can easily end up with a deadlock in this case because the process waiting on B still holds the lock for A. So like, for example, if the only way for a notify to happen is to also take out the lock for A, then you're going to have a deadlock. And even if you don't have a deadlock, you may just be messing up the throughput on your system because you're spending a lot of time with a lock for A being taken out unnecessarily because maybe there isn't actually any need for A in this situation. So one common sort of tip that people would give, if you Google nested monitor lockout, there's a bunch of web pages being like, there's a problem, here's how to solve it. And one piece of advice people will give is, when you're writing Java code, make sure you don't do blocking calls inside of synchronized methods. So for example, if you have a class, you might have both a synchronized version and an unsynchronized version of the method, and you might be able to call the unsynchronized version instead, so you don't take out that inner lock in that situation. Now, this doesn't always work, right? Like, you'd only be able to unsynchronize a method if you didn't actually need the critical region protection in that case. And in general, that may not be true. There's a question here. Is there a way to actually fix this scenario? Do we have to combine A and B into a single monitor? That's a good question. Let me see. Did I write anything here? No, I didn't write anything here. So how to actually fix this code is very context dependent. So one way to fix this code is to just manually rewrite it so that you release both the locks for A and B when the wait happens. This can be okay. In particular, it can be okay if the state of A, while you're inside the critical region, is sort of in a safe point where it's okay for other threads to observe this intermediate state. Because one thing you have to be careful about when you wait is that you are going to release the lock. So if you did a bunch of intermediate work in the object and you weren't sure if this work was going to be if this work is just if the class is in some sort of messy, half initialized state, right? Say there were 50 fields and you needed to update and you'd updated 25 of them, but not the other 25. Well, that would be bad if you release the lock and then let other people see, your dirty laundry. But if everything is safe, then you can just release both A and B in this case. Another way to solve this problem is to combine the locks into a single monitor that will serialize your code some more, right? In general, any situation where you have multiple locks, you can replace them with a single lock that protects all of the code in question, right? And that just means you have more contention in your system. And so if the locks aren't very hot, that might be very good and very simple way of implementing things. Actually, when we talk about how STM is implemented later, there's actually two strategies. There's a fine-grained locking scheme where we lock every object that's participating. And there's also a big global hammer lock, which when we want to do a transaction update, we just take that lock and then update everything in that situation. We don't try to do anything fine-grained. And sometimes that's okay, especially if it's not hot, or maybe the inside of the critical region is very fast to execute. So it doesn't matter that you have a single global honking lock. Thanks for the question. Nice question. So to summarize monitors, monitors you can think of are a basic programming discipline that happens to have a little bit of built-in syntax in Java that takes to heart the advice, which is that when you define a lock, it should be associated with some data. And so it just makes it very easy to say, okay, I have some data and it is associated with a lock, hooray. But, although it is simple to implement, that doesn't mean it's necessarily simple to use, right? So it can get you into trouble with nested monitor lockout, and it can get you into trouble because when you actually want to write your code, monitors might not be an exact fit, and so you end up writing some complicated code to shoehorn everything into the monitor style. There's also some other problems which I didn't really talk about. One problem is the so-called lost notifications problem. So the way that notify works in Java is it just says, okay, given the current state of any waiters on this object, I will wake one of them up. But there's a problem, which is, let's say that you do a notify and no one is waiting for you yet because you actually raced and the person who was about to wait only comes in after you did the notify call. If you're not careful and that call doesn't properly check that actually it can go immediately, you can end up in a situation where you end up with a thread waiting for a notification, but the notification already happened before that object had started waiting in the first place. So you got to be careful when you're writing Java code that way as well. It's easy to make this mistake if you're doing complicated stuff. There's no way to set priorities on these locks, so you just have to make sure you design your system carefully not to accidentally starve important resources. And of course, you can still deadlock, right? Synchronized blocks are just locks. So you can just as easily deadlock by taking out, 2 synchronized blocks in the wrong order. Okay, that's everything I wanted to say about monitors. Any more questions about monitors? All right, so let's look at a very different approach. But this approach is very practical. And if you are ever in a situation where you need to write a concurrent system, a concurrent system in a sort of normal imperative programming language, I highly encourage you to consider writing it in this style. So the message passing style flips the idea on its head. So Java monitors were all about, well, we've got these objects. These objects are shared across threads. They have shared mutable state, therefore, and now I need some locking scheme when I want to access this shared data. Message passing goes the opposite route. It says, hey, when I write my code, I'm just going to not actually ever share any state between threads at all. So I will never have an object which might secretly be referenced by some other thread, and therefore I have to take out locks before I access data on it. Instead, if I want to communicate through other threads, I have to do so via a highly specialized mechanism called message passing, where, for example, if I want to access some data, I say, hey, monitor, I want to access some data through the requiem method, and the monitor will send me a response in this case, right? So I actually can rewrite all of my traditional locking stuff as messages, but you probably don't want to do it this way because messages let you do a lot more. So there's 2 models for message passing, and the way that I would distinguish them is basically whether or not they are so-called asynchronous or synchronous. So asynchronous message passing is kind of like, how the post office works, right? You want to send someone a letter, so you put your letter in your mailbox, and then at some indeterminate future point in time, that letter eventually makes it to its destination. And that destination mailbox can have as many, letters in it as you want, right? You can send as much stuff as you want, and eventually the person will get it and process their mail. So it's called asynchronous because there's no waiting involved. You just send messages, and they get buffered at the receiver until the receiver is actually able to handle it. Erlang is an example of a very well-developed message passing system that is asynchronous. The other method for message passing is so-called synchronous message passing, also known as the communicating sequential processes model. And in this model, it's a lot more like doing a handshake between 2 processes. So, one process says, okay, I'm ready to receive the data. And the other process says, okay, here is the data. And once again, they're doing these with messages, so there's no intrinsic shared state. But for example, if you wanted to send a piece of data, you would have to wait until the receiving process was ready to accept it. So none of this, tossing a letter over the fence and then going off and doing other stuff. You're going to wait until they're ready. So Haskell supports synchronous message passing via an abstraction called mvars. Mvars are great. More languages should have mvars. The way to think about mvars are they are a one-place concurrent buffer. They're one place because the buffer only ever holds enough data to store a single item. And so if the buffer is full, well, too bad for you. You're going to have to wait to put things into the buffer. So let me conjure back some Haskell syntax in your minds. So mvar is a data type. It can store anything. So it's a type parameter that takes in an A saying what it stores. And there's a number of operations we can do on them. New empty mvar allocates a new mvar that doesn't have anything in it, right? So it's ready to accept data. Mvars live in the IO monad because, like IO refs, they are mutable state. You can change them after the fact. So allocating a new cell for mutable state should also be in the IO monad. There's also new mvar, which takes in a value and it allocates the mvar directly with that value stored inside it. And then you have take and put mvar. Take mvar, takes out a value from the mvar if it's full, whereas put mvar puts a value into the mvar if it is empty. So there's a few different sort of configurations for mvar and putting and taking that are worth stepping through. So let's suppose that I call put mvar with some value. That's what my little dot arrow thing is. It's just a pointer to a value on the heap. And I have a mvar box, which is empty. So if the box is empty, I can immediately just put the value into the box, and now I have a box with a value in it. However, if I have a mvar which already has a value in its box, I will block. And I will wait until that mvar gets vacated, until that value is taken out, so that I can actually put my value in. So I'll do no more work until I actually see that the mvar has cleared up. Conversely, take mvar when passed an empty mvar will block because there's no data to actually return in the situation. You just have to wait until someone gives you something. And similarly, if there is actually data in the mvar at this point in time, we just immediately return that, clearing out the mvar in this case. Does this sound very similar to wait and notify? Basically, mvars are a very stylized use of wait and notify, with this particular set of semantics. So you could implement mvars in Java, and one of my previous year exam questions was exactly that. They asked you to implement mvars in Java. So you might be like, hey Ed, that's cool. I like mvars, but this one place buffer thing is a bit of a drag, right? What if I want to store a lot of values? And the answer is actually, you can do that too. You just need more than one mvar. So the model for message passing with multiple mvars is we implement this thing called a channel. And the way the channel works is we will in fact represent it as a linked list of mvars with a pair of mvars pointing us to the beginning and the end of the list. So in this picture, the black mvars are boxes. The black boxes are mvars, and the blue boxes are just traditional Haskell data structures. So this would be our data structure representing the channel with its head mvar and its tail mvar, and then these blue boxes would be like list cells containing the value as well as pointer to the next mvar in the list in question. So let's just take a look at how you would actually, for example, pop something off the channel. So what I would do is I will first take out the value pointed to by the is this the head or the tail of the list? The tail of the list. Well, we'll take out that pointer from the tail of the list, right? So now we've got the pointer to the tail of the list. Importantly, no one else has the pointer to the tail of the list because this mvar is now empty. If anyone else tries to access this, they will have to wait until I put a value back into this box. So the mvar can be used as a very simple form of locking, right? Where you take something out of the box when you want the lock and you put it back into the box when you want to provide the lock. Then what we'll go ahead and read out the value from this mvar, giving you back this first value. And then once we've given back that first value, we go ahead and repopulate the box with a new pointer to the tail mvar of the box in question. So now I have a channel, but it only has one element on it. Questions about how this channel implementation works? Pushing a new element onto the channel here is pretty similar, by the way. Okay, so let's talk about message passing in general. So the big benefit of message passing is it's very, very, very simple, right? Like all this stuff about like, monitors and waits and notifies and message, doing things. It sort of all evaporates when you're doing message passing, because with message passing, there's just a fixed set of allowed messages that you're allowed to pass between processes. And all the complexity comes in sort of defining what those messages are. The actual message passing is very simple. You just, send the message and the process handles it when they get to it. In fact, the term communicating sequential processes, you probably will never hear people use that in actual implementation, but that's basically a sort of theoretical model for concurrent communication. And, people like define a formal model the same way we would define like type checking as a formal model, and then study some of its properties. So it's simple enough that it can be the basis for theoretical programs. There's a question which is, can mvars be implemented without using any locks? And the answer is no. Right? So I said at the beginning of this lecture that locks are going to be like this core fundamental primitive for doing concurrent programming, and a lot of higher level things are going to be built on top of it. And message passing is no exception. To actually do message passing, unless you're going to actually like use atomics, which kind of are using locks, just down at the processor level, you are going to actually need some amount of locking. And in particular, the lock here is when we're actually trying to read out an element from the mvar itself. We have to take out the lock and then read it out and then fill it in and then release the lock. So because every mvar constitutes a sort of one-place lock, it's still easy to deadlock when you're using mvars. There's a question which is, getting to the nth element in the channel would require you to walk through the channel. That's true, although typically if you have a channel, you're just interested in getting the next element, right? That's available for you. So you're going to read them off sequentially one by one, popping them off the channel. So we did synchronous messaging in a lot of detail with mvars, but with asynchronous messaging, there's sort of like different set of challenges. So one of the big challenges with buffer-based concurrent programming is you have this big question, which is, how big should the buffer be? A bad answer to this, by the way, is it should be allowed to grow unboundedly. And this is a bad answer because if you're in some sort of performance crunch situation where like your producer thread is using way more messages than your consumer thread can deal with, your buffer is just going to grow bigger and bigger and bigger, and your application runs out of memory, or you just fail to like ever respond to any messages because your buffer is just too big and all the new requests are getting stuck inside this large buffer. So dealing with like buffer sizing, that's kind of a big problem and sort of one of the like very artistic parts of working with an asynchronous messaging system. If you want to learn how to do this well, Erlang has a lot of good practices on this because they're all about asynchronous messaging. So definitely would read up about Erlang. There's also like this theoretical problem with asynchronous messaging called unbounded determinism, non-determinism, which basically says, actually, I don't remember. So ask me in office hours if you want to know more about that. It's not that important. It's like a theory problem. CSP, very easy theory. Async message passing, not so easy to model theoretically. By the way, something I need to say about message passing. When you send a message, you have to not then read or write out of it, right? Like you give your message to the other thread and that other thread now has the message. You can't just rip the envelope out of their hands and go ahead and start making modifications to the message, right? Like that's not how things work. And so to actually enforce this, because programmers are the kind of critters who will figure out how to do something naughty if you let them do it, there are lots of different ways of dealing with this problem, right? So for example, Erlang actually will have each of their concurrent processes have a separate address space, so it's just literally impossible to access the other the data once you've sent it over to another thread. And like this also makes failure recovery in Erlang a little easier because you've got these separate address spaces, and if one of them crashes, you can reboot it and like have all the other parts of your system still running. In Haskell, we said Haskell is a purely functional data programming language, and that means in Haskell, by default, all of our data is immutable, right? So it doesn't matter if I pass some data off to another thread, I still can't mutate it. So the thread will always be able to see a consistent picture of the story. Although, that being said, Haskell does have lazy evaluation. Lazy evaluation is a form of mutation, although it's not sort of observable, functionally speaking. But laziness can actually cause weird performance problems in multi-threaded systems where you like do a computation on one thread and you pass it to the other thread, and somehow your other thread is like running very slowly, and you debug and you find out that's because you didn't actually do the work on the first thread. You just wrote a thunk and you passed it over to the second thread, and your second thread is like sweating trying to do all the computational work that your first thread was supposed to do. Oof. Not a good idea, right? So dealing with laziness when you're doing concurrent programming can be a bit tricky because it does have this mutable state. Granted, it can't change the behavior of your program, but it can certainly change the performance characteristics of your program. And the last thing is you can send a message that's mutable if you promise never to like touch it again, right? And this goes to this concept of ownership where like I own some data, and then once I transfer it to another thread, I no longer own that data. And only the person who owns that data is allowed to actually make mutations on this. And in this way, I can avoid having to make all my data structures immutable, and I can avoid having to separate them into an address space. I basically am saying, hey, all I need to do is make sure that I don't use stuff after I've given ownership to it. And if you're Rust, you've got a type system that you can actually use to make sure you don't do anything naughty. If you're C++, you also kind of have a type system, but it's not sound and it's not going to catch all errors. And basically writing concurrent code in C++ is like juggling chainsaws. Like there's so much stuff you have to keep in your head when you are doing stuff in C++. So a lot of people write Rust because it's just too hard to write concurrent. This is where the moniker fearless concurrency in Rust comes from. There's a question. So with Rust, when sending the message, you also transfer ownership. Well, I mean, Rust lets you do a lot of stuff. But one of the most common ways of passing things to other threads is by giving up ownership when you do the transfer in that case. Okay, so I want to talk about another idea. So immutable data, right, is kind of very nice and easy to work with. In Haskell, we have most of our data structures being immutable, and immutable data can, be freely shared between threads because it's always the same thing, right? It never changes. So there's no possibility of, stomping over each other's toes in this situation. Deterministic parallelism. Sorry, I guess that was it for this slide. Sorry. Okay, I want to talk about another idea called deterministic parallelism. The idea behind deterministic parallelism is that, hey, we've been talking all about this concurrency thing, which is all about, multiple threads running at the same time. But there's another concept, which is, I have some code and I just want it to run faster. And how am I going to have it run faster? Well, the idea is let's say that I'm processing this large batch file, and it actually is very parallel because I'm just doing the same operation for each entry. I might want to just, run all of those in parallel and get my result faster than I would have been able to get otherwise. So concurrency is all about, this idea of availability and interactivity. It's all about modeling the real world. It's about like embracing the non-determinism that happens when you have multiple things going on at the same time. But parallelism doesn't necessarily have to do anything with this, right? All you care about is running your code faster, distributing the work over multiple threads. And what this means is if you're a programming language designer or you're a library designer and you only care about parallelism, you only care about making stuff run faster in a more distributed fashion, and you don't care about like actually dealing with the non-deterministic events, stuff flowing in at arbitrary intervals, you can design things so that you get parallelism, but you don't actually provide a concurrent interface. You don't have any locks, you don't have any non-determinism, you just give an API that lets things run in parallel without being able to observe all the nasty concurrency bits. Similarly, by the way, you can have concurrent programming without actually truly running things all at the same time. And actually, our lab is in JavaScript. It's about concurrency in JavaScript, and there will be no multi-threading involved. Instead, we'll just be using continuations to manually handle the scheduling ourselves. So your lab will run deterministically, but all the problems about shared resource access, they still apply because even though you're running deterministically, there are still multiple logical threads of execution going on, and whenever you yield to another thread, that thread could stomp over the state that you were expecting to be able to work with. So JavaScript in general, right, lets you do lots of things seemingly at the same time, but JavaScript doesn't let you actually run with multiple threads. It's just because your computer is so fast, it gives the illusion that multiple things are going on at the same time. So going back to deterministic parallelism, the goal of deterministic parallelism is to let you speed up your code without having to deal with locks, right? And so I talked about like this batch data processing thing. And so systems like MapReduce are exactly all about this, right? They're all about you just define your map function, you define your reduce function, and then you will magically distribute it in a parallel way to like run quickly on a big data set. But the code you wrote was like just purely functional, right? You just said how to do the mapping, how to do the reducing. You didn't have to worry about locks. You didn't have to worry about concurrency. The framework took care of that all for you. And there's all sorts of other interesting research ideas like, using lazy evaluation to parallelize your execution. This is something that GHC did some research on. And there's also other ideas about like, for example, so-called monotonic data structures where, so we do want a little bit of cooperation between the threads, but we'll do so in a way where the state of the world only becomes monotonically more well-defined. And when you write your programs this way, you eliminate the ability for non-determinism to creep in. This is like, I could spend an entire lecture on this, so I'm not. But if you want to read more about it, like you can check out Lindsay Cooper's work on LVARs, for example, which are this kind of idea. Oh, I'm so behind schedule on this lecture. I might talk a little bit about memory models on Wednesday before we move into STM. So this is what I'm going to talk about on Wednesday. I'm not going to talk about it at all, but because we're gonna dedicate time to it on Wednesday. Okay, so let's see how many slides. Okay, let's do memory models. I'm not sure if I'll finish this, but I've got 12 minutes, so maybe I can. So we spent a lot of time talking about high-level ideas built on top of locks, but at the end of the day, we need to actually say something about locks. We need to say something about hardware. We need to say something about the languages ourselves, and that's going to be what memory models are about. In other words, memory models tell us what our programs do when they have data races. And let me just talk a little bit about what I mean by data race. So let's imagine that we've got two threads, and they're accessing some shared data, x and y. And so thread 1 sets x equal to 1, and then temp1 equal to y. And thread 2 sets y equal to 1, and then temp2 equal to x. And there's no locks, there's no synchronization. So, the question at hand is, if I write this code and I don't have any locking, what values of temp1 and temp2 are allowed? Let's suppose that x and y are initially 0. So the memory model is what we have to call in to answer this question in the situation. So how we answer this question depends on the context, right? So for example, when I write code on the JVM, the JVM has a memory model. And so it has one particular answer for this question. If I compile this code into x86 machine code, that is also code that I can run, and our processor also gives us some sorts of guarantees for the situation as well. So here is a very simple memory model that you might naively think is the case when reasoning about concurrent code. And this memory model is called sequential consistency. The idea behind sequential consistency is that if we want to understand what this program does, we imagine that each of these instructions is a sort of like atomic instruction. And the only concurrency can happen is by re-interleaving these instructions in some order. So for example, first I ran x equal to 1, then I ran y equals 1, then I run temp1 equals y, then I run temp2 equals x. So the picture for that, right, is you got these threads and they're like transmitting these assignments and reads into some shared memory. And this is very simple, very easy to reason about. Well, not that easy to reason about, but like if you look at some source code, this is the first thing you would do when trying to reason about what happened in the data race situation. And in fact, no one does this, right? You will never, ever, ever get a programming language or a instruction set that implements sequential consistency. In reality, there's more stuff going on. So on x86, for example, x86 has a more complicated model called total store order, where there are write buffers associated with threads. So when you write to memory inside a thread in x86, it doesn't go straight to shared memory. Instead, it hits a local write buffer, which eventually gets cleared to the memory at some later point in time. It's guaranteed to happen eventually, and there are other instructions like lock or flush, which will immediately flush the write buffer to shared memory. The model for x86 total store order works like this. This is good to know. It's not that complicated, which is that buffers are first in, first out. So if I put something on the buffer and there's nothing else on the buffer, that write is going to be the next write that eventually gets committed into memory. Furthermore, if I've written to my buffer like x, and then I do a read on x immediately thereafter, I will service that read from the buffer instead of going all the way to main memory. That's good for efficiency because going to main memory is expensive and the buffer is local to the processor, so it's cheap. Then the mfence instruction flushes the buffer. And locked instructions take out a global lock. So there's a global lock associated with your processor. And once it's gotten the lock, it can do a bunch of operations. And then at the end of the locked region, everything gets flushed to main memory. And when you take out the lock, you basically don't buffer your writes. When you take out the lock, other threads are not allowed to buffer push their buffered writes into main memory. You've got exclusive access, and you get to do your stuff without worrying about consistency. So by the way, you can't actually take out this lock. Instead, various instructions are locked, and so the instruction will proceed without anyone else being able to clobber the memory, and then everyone else can go. Because if you could take out this lock, that would be pretty insane. 6 minutes left. Okay, so I want to go back to this example, and I just want to spend a little bit of time thinking about what we thought this program might be able to do. So when we looked at this in source code, and when we thought about it as sequential consistency, there were a few situations that we thought could happen, right? So one obvious happy situation is thread 1 runs all the way to the end, and then thread 2 runs all the way to the end, right? In that situation, temp1 would be 0 because y hasn't executed yet. And then temp2 would be 1. Similarly, you could run them in the other order and you'd get 1 and 0. And that seems also very reasonable. And you also might imagine a case where these threads race. So they both set x and y to 1 before reading out their temporaries. In that case, you would read out 1 and 1. So the question at hand is whether or not 0 and 0 is a possible state. And in fact, in sequential consistency, it's impossible, right? In order for us to get to this temp1 read, we had to actually go ahead and execute x equals 1, which would cause this temp2 read to read out 1, right? So I can't both read out 0 here and read out 0 there, because this implies that one of these instructions actually had already executed at that point in time. Not so, though, when you are in total store order model. So let's look at what this code does in TSO. So in TSO, what we can do is we can buffer the writes to x and y on both of the threads. So they don't go to main memory. Instead, they are hanging out in the buffers in question. Then I can go ahead and do a read. These reads don't hit any writes in the buffer, so they go straight to main memory, and we read out what the values on the main memory are, namely 0 and 0. And therefore, we read out both 0 and 0 for the temporaries before the writes get flushed to main memory. So in x86 TSO, it is possible to get 0, 0 when running this assembly together. This is a critical point, so I just want to check if there are questions. Here is a fun example from a research paper about x86 TSO. It's basically the paper that defined TSO in a formal way for understanding x86 semantics. Before then, it was like a pile of like indecipherable Intel manual stuff. And here's the implementation of spin locks in the Linux kernel. And basically what the paper does is it walks through the reasoning for the code here and then reasons out that it's okay for this final move instruction to not be locked. It's very involved, but once you have this model in your head, you can basically reason it out step by step. Now, ARM is a very popular architecture these days because your M1 MacBooks are running it, and ARM is a different instruction set and it has a different memory model. And in the ARM memory model, you don't even have this assumption of there's this buffer, but the buffers have to be in order. In ARM, your reads and writes can be completely out of order, and when you do a write, it may become visible to some threads, but not others at some point in time. So there's a formal description of the ARM memory model, which I don't have time to do in lecture today, but it's more relaxed than x86. And so code that previously worked perfectly fine 100% of the time in x86 could in fact be buggy on ARM because it gives less guarantees about the memory model. I'm not going to get into Java memory model. Okay, so next time I will talk about the Java memory model and then hop to software transactional memory before I get there. I do want to talk about the Java memory model because it is important. So in the last 2 minutes, any questions about concurrency in general? I guess I can give the preamble text for this. So the preamble text for this is, we talked about hardware architecture memory model. So this is talking about what's going on when you run assembly instructions. But this is not, how things run on hardware is not the only way that you can influence how your program executes when you are running it. For example, when I have some programming language, some high-level programming language, and I want to run it, I first compile it to the hardware architecture. And this compilation process can also result in observable differences when I run code concurrently, right? I can, for example, eliminate a store to a variable because it's never used anymore, right? And that store might actually have been visible from another thread, but because it's not used, I got rid of it, and now the store is no longer visible. So a language also needs to provide a memory model in this situation. Okay, we are out of time. Thank you very much, and see you all on Wednesday.